Uh, Good afternoon, everyone. My name is Katarzyna Ochromowicz. I will be presenting our results on solvent extraction of lithium from brine solutions. And I want to focus mostly on the methodologies we used, on challenges that occurred during realization of our task, and of course, on findings. Let me begin with the composition of the brine we worked with. It was natural Galki brine containing around 65 ppm of lithium and significantly higher concentrations of sodium, calcium, and magnesium. It was the only natural brine available for the studies, as other solutions, other brines collected during the project contained much less lithium. And if we want to think about recovery of lithium, we had to think about concentration of lithium, and we decided to initially pre-concentrate lithium by evaporation to the level of 500 ppm, and then by the use of solvent extraction to the target level 6 grams per liter. This target level is related to solubility of lithium carbonate, which is around 2.5 grams per liter. So we wanted to obtain some small portion of lithium carbonate after successful extraction. We were also using synthetic solutions, semi-synthetic by mixing, by doping lithium to natural brines, just to have opportunity to work with solutions differing in lithium concentration, so to study wider range of conditions. Here you can see our experimental concept on recovery of lithium by a combination of evaporation and solvent extraction. And our goal here was to obtain pure and concentrated lithium solution from which lithium carbonate could be precipitated. And our main focus was on solvent extraction, on finding a proper extraction system, something that allow us to extract lithium from different brines and recover it back later in stripping stage. And based on literature review, we selected two commonly used extraction systems. First one was based on the mixture of tributyl phosphate and metal isobutyl ketone, and we worked with this system last year. And the second one was the mixture of trioxylphosphine oxides and beta-decatone. And for both systems, we wanted to optimize extraction parameters, extraction results by adjusting key factors listed on the slide. And here, just a short reminding of previous year's results. We were working with TBP MIBK system. And this system was selected for lithium. We were able to reach 90% extraction regardless the diluent used. However, to reach this number, we had to use co-extractants. We had to introduce iron and aluminum chlorides to the brine. And these results were obtained only for synthetic solutions. When we repeated these conditions and we used natural evaporated brine, the efficiency dropped to around 30%. And we also noticed some difficulties with before extraction and during extraction, we noticed the precipitate. And it was inconvenient for us because we have to plan another cleaning step before extraction and after this stage. So we decided to abandon the system and switch to the second one. The main difference between those two systems was lack of selectivity for lithium. So it was our challenge we had to cope with this somehow. Besides, we wanted to know whether this system could effectively extract lithium, whether it will be possible to strip lithium from organic phase, and whether it will be possible to concentrate lithium to this target level by changing volumes of aqueous and organic phases during extraction and stripping. And to address the first challenge, lack of selectivity, we decided to modify our experimental concept a bit by introducing additional cleaning step before evaporation. I don't know where the precipitation. We decided that we had to remove contaminating ions, calcium and magnesium here, because the concentrations of calcium and magnesium were pretty high. So we wanted to remove divalent ions because our system could extract them together with lithium. Alternatively, some other method could be used, for example, selective separation by ion exchange, but it was beyond the scope of our study. Okay. And this new approach involved precipitation of sparingly soluble compounds, and we considered precipitation of oxalates or hydroxides. When we look at the numbers, we can see that we could expect that lithium would remain in solution because solubilities of its compounds are, we can say that are high comparing to remaining ions. And if we go through oxalates route, we could expect that we can almost totally eliminate calcium, and some portion of magnesium would remain in solution. On the other hand, if we go through hydroxide route, we could expect that magnesium could be nearly completely precipitated, but a substantial portion of calcium will remain in solution. Because we wanted to remove both ions, we decided to use both ways, and we tested two sequences of successive precipitation. First one, hydroxides followed by oxalates. In this case, we added solid sodium hydroxide or its solution to Brine to first precipitate calcium and magnesium hydroxides, and then after phase separation, we added oxalic acid to further precipitate calcium in the form of oxalates. And we ended up with neutral brine. In the other sequence, we first added oxalic acid to the brine to precipitate calcium and magnesium oxalates, and then sodium hydroxide after phase separation. We added sodium hydroxide to further precipitate remaining magnesium in the form of hydroxides. And in this case, our final brine was alkaline with pH around 12. So this is the main difference between those two sequences. And we also noticed that the reagent consumption differ, and in the case of hydroxide oxalate sequence, we observe lower reagents consumption, so we can say that this route is more economical. But in the context of further processing, in the context of dealing with this brine, we decided to evaporate this brine to concentrate lithium, and then to lead it to solvent extraction. And in the context of solvent extraction, pH is very important, and let me show you why by showing you the results of extraction experiments. We have run several experiments changing aqueous phase composition by using synthetic, semi-synthetic, and natural brines. We are also changing organic phase composition, but we found out that the most important parameter deciding of extraction efficiency was equilibrium pH. This is the pH of aqueous phase after extraction, after contact with organic. And as you can see, the higher this equilibrium pH, the better the results. And we were able to reach 99% of lithium extraction under condition that our equilibrium pH was at least 9. One way to ensure this high value of equilibrium pH is to introduce alkaline brine to solvent extraction, to extraction stage. So going back to the pretreatment, we think that oxalates hydroxide sequence is a better option. But we also have a solution for neutral brines, and I will show you this in a while. Okay, so we were able to answer the question whether it will be possible to effectively extract lithium, and we know, yes, this is possible. But good extraction is only half success. We don't want to leave lithium in organic phase. We want to recover it back. So our next challenge was whether it will be possible to strip lithium from loaded organic. And here we used solutions of sulfuric acid, and as you can see, 1 mole solution gave the best result, recovering almost 75% of lithium in a single stripping stage. So it was very good result. However, we noticed some difficulties with phase separation due to formation of emulsion. It was very stable. In some experiments, phase separation lasted for a few hours, in other few days even. So it was a huge problem, huge challenge for us. We have tried different approaches to cope with this issue. And we noticed that the double stripping helps a bit, but only in visual look of organic phase. As you can see in these pictures, organic is milky white or hazy, and this is the situation where phases are separated. But double stripping can help in the look of organic, but it's still phase separation time were still long. This is the double stripping is of course good because we can increase lithium recovery. As you can see, 75% in first stage and another 50% in second stage. But we tried to do something else. We decided to use alkalized organic phase instead of alkaline brine. So we had to saponify organic somehow, and we contacted fresh organic phase with sodium hydroxide solution. After phase separation, this saponified organic was contacted with neutral brines. So this is the problem with these neutral brines coming from hydroxides oxalate sequence. As you can see, we were able to almost completely extract lithium from brines, and depending on saponification ratio, we were able to maintain this good stripping efficiency also. And in this case, we noticed that phase separation was quite quick, in some situations even rapid. So we were able to for that moment, fight with this emulsion, we decided that this is the best option we can do to get rid of this. However, the organic phase was still milky or hazy, but at least phases could separate quickly. Okay, so we know that this is possible to extract lithium effectively. We can strip it back, and the final question was whether it will be possible to concentrate lithium to reach our target level. And to answer this question, we decided to contact aqueous and organic under different volumes. And we generated extraction isotherm. This blue line is our extraction isotherm, and based on this isotherm, we constructed McCabe-Thiele diagram. This diagram shows that we are able to almost completely extract lithium from the brine in two extraction stages. And at the same time, we can saturate organic phase to the level of around 500 ppm. So we can transfer lithium from the aqueous phase to organic, increase its concentration, but aqueous to organic volume ratio is here 10:1. So we must use excess of aqueous to reach this concentration. So we expected that by adjusting these volume ratios in stripping, we could receive solutions containing at least 6 grams per liter of lithium. And this is good option for low-grade brines like Garki containing around 50 ppm of lithium. We can see that solvent extraction has potential to concentrate lithium from low-grade brines. However, we must remember that this is good option where we work on clean solutions, brines that are not contaminated. Moreover, we must remember that to obtain sufficient volume of solution after stripping to precipitation of lithium carbonate, we must use large volumes of original brines. And for this reason, we couldn't explore this approach further because we have limited volumes of brines available for the studies. But eventually, we have run several tests to check whether we will be able to reach this target level. And here you can see the summary of our results. First test, this one. Yeah, the first test was conducted on alkaline brine. It was synthetic solution containing around 500 ppm of lithium, and we decided to check whether excess of organic over aqueous in stripping would increase lithium concentration. And as you can see, we were able to obtain solution containing around 1.3 grams per liter of lithium. In our next experiment, we used natural brine after calcium and magnesium removal and after evaporation. And it was also alkaline brine from this oxalate hydroxide sequence. And as you can see, we were able to increase lithium concentration to 4.6 grams per liter, still below the target. And later we decided to check how saponified organic will work. And as you can see, in this second test, we were using threefold excess of aqueous over organic in extraction and fivefold excess of organic over aqueous in stripping stage. and we were able to obtain solution containing 3.5 grams per liter of lithium. And this result was weaker than earlier, but when we compare equilibrium pH, we can see that this is the main problem. The saponification of organic phase was not so optimal, probably. And we decided to still use the saponified organic, but we decided to increase excess of aqueous to 4 in extraction and excess of organic to 10 in stripping stage. And as you can see, we were able to obtain solution containing around 9 grams per liter of lithium. So we exceeded our target level. However, this result was obtained for synthetic solution containing only lithium. When we repeated these conditions and we used natural galky brine, as you can see, we observe minimal extraction. And when we see the pH equilibrium values were below 8, so we couldn't expect a higher extraction. But we can say that solvent extraction, based on these results, we can say that solvent extraction has potential to concentrate lithium from low-grade solutions to much higher levels. However, we must keep an eye on equilibrium pH, and we must remember to introduce purified solutions to extraction stage. And concluding, we can say definitely that Mextral topo system can effectively extract lithium, and it can be used to concentrate lithium for purified solutions. But generally, solvent extraction is a suitable method for various solutions differing in lithium concentration, and it can be optimized by adjusting parameters like pH, like volume phase ratios, and composition of organic phase. We can also say that this method has potential for scaling up, and it is possible to ensure that this process works fine on a larger scale, but we must carefully optimize process conditions. And the last conclusion, I think that also important, that the results from laboratory scale tests cannot be transferred to larger scale. We cannot reliably predict process kinetics or energy consumption in larger scale based on our laboratory results. These factors must be carefully evaluated through pilot scale testing. Thank you very much for attention.